Okay, energy, heat capacity calculations. Of course, you know, we've got these things we can measure, then we have to do all these dumb calculations, right? So here is the equation. In words, the heat, the energy, equals the mass times the specific heat capacity times the temperature change. In letters, Q equals mc delta T. So Q is the amount of heat in joules, m is the mass in grams, C is the specific heat capacity in joules per gram degree Celsius. That's something that if they don't give it to you, you may have to go look it up in that table. T means temperature. There's actually something missing there. This should be delta T, is the temperature change. And delta T means T final minus T initial. So anytime we see delta something, delta means change in. And you always take the final and you subtract the initial. Because if you're climbing a hill and you're looking for your change in altitude, you take your final altitude minus your initial altitude. You went up. That's a positive number, right? If you're descending, then your change in altitude would be negative. So sometimes these signs matter. So we're going to do a lot of examples. This one's got a lot of words in it. You find a copper penny, pre-1982, in the snow and pick it up. How much heat is absorbed by the penny as it warms from the temperature of the snow, minus 5 degrees Celsius, to the temperature of your body, 37 degrees Celsius? Assume the penny is pure copper and has a mass of 3.10 grams. You can find the heat capacity of copper in table 3.4 on page 74. Well, before we start writing on this slide, let's go back and find the heat capacity, since they specifically said you're going to need that. So here, copper, 0.385, and the units are important, joules per gram degree Celsius. Okay, so I'm just going to write that down. Hopefully I can do that before it leaves my brain. 0.38, is it 5? 5? Yes. Okay, joules per gram degree Celsius. And I'm saying joules. So my husband and I have been watching Psych, and that's what Sean calls Juliet. He calls her joules. So I keep thinking of this TV show when I'm saying energy units. Sorry. Okay. There's a lot of words in this problem. We need to take the numbers and make some sense out of them. Okay, this number up here, pre-1982. Do you think we need to use a year in our calculation? Probably not. Why did they throw that in there at all? Well, before 1982, pennies were solid copper. Now pennies are not solid copper. They're zinc with just a thin layer of copper on the outside, because even so, the pennies are worth more than a penny. So we don't need that one. We need these other numbers, though. 37 degrees Celsius minus 5 degrees Celsius, 3.10 grams. And those are the numbers, right? So let's put these in here. 3.10 grams. That is the mass, right? It even says that right here. Mass of. Okay, so that is M. And then we've got two different temperatures here. So this temperature, minus 5.0, is that the final temperature or the initial temperature? That's initial. It warms from the temperature of the snow to the temperature of your body. So that's the initial temperature. And then the 37 must be the final temperature. So now we've taken the numbers out. Now what are they wanting? How much heat? How much heat? Well, that equation that we had was Q equals mc delta T. Q is heat. I know you probably think it should be H. It's always Q, I don't know why. Q is heat. So to find the heat, we need the mass, and they gave us that. We need the specific heat capacity. They told us to look it up, so we did. And we need delta T. Do we have delta T yet? Not quite. I'm going to do that up here in the blue bar. Delta T is the final temperature minus the initial temperature. So that would be 37.0 minus -5. And that ends up being 42. Does that make sense? Now we have M, C, and delta T. We're just going to put them all together. Q equals the mass, 3.10 grams. Always write the units. Times the specific heat capacity, 0.385 joules over grams degrees Celsius, times the change in temperature, 42 degrees Celsius. Before you do the math, check the units. Grams cancel grams, Celsius cancels Celsius. I'm left with joules, unit of energy. That's a good sign. 3.1 times 0.385 times 42. Calculator says 50.127. Joules. Awesome. Sig figs. Well, let's look at the temperatures. 37.0 has 1 decimal place. 5.0 has 1 decimal place. So then the difference should have 1 decimal place. So that one, the reason I wrote 42.0 is because that first decimal place is a significant figure. So then that tells us that here, 42.0 has 3 significant figures, 0.385 has 3, and 3.10 has 3. So my answer here should have 3 significant figures, so I'm going to call it 50.1 joules. Any questions? Well, 3.10 has 3, and 0.385 has 3. And so then the temperature is something we have to look at. The temperature, we got that 42 from this temperature and this temperature. And yes, 5.0 only has 2 significant figures. But how did we get the 42? We got it by subtracting. The rule for subtraction is that you look at the number of decimal places, not the number of significant figures. This has 1 decimal place. This has 1 decimal place. So our answer has 1 decimal place, regardless of the number of sig figs. Does that help? Now, on a problem like this, on an exam, I'm not out to trick you with the significant figures in the answers. There would, it's going to be multiple choice. I would not have 50.1 and 50.127 both as possible answers. Okay? But we are going to practice using significant figures all the semester long. Any other questions? Yes?
It's not joules over grams or joules per grams per degree Celsius because you cancel them out, right?
Right. Because in this term we had joules divided by grams divided by degrees Celsius. But when we multiply by grams, the units cancel out. And then we multiply by Celsius, and the units cancel out. And that's why specific heat capacity has that weird unit of joules per gram degree Celsius. This is one of those situations where if you didn't remember the actual equation, the units give you huge clues. You can just take these numbers and, well, how can we put these together so the units cancel out? And you could probably come up with 50.1 as an answer. Any other questions? This is a straightforward problem where they give you mass, you have to look up specific heat, give you two temperatures, calculate Q. So sometimes we have to rearrange the equation. So we'll do some of those too. A lead fishing weight with a mass of 75 grams absorbs 146 calories of heat. If its initial temperature is 47 degrees Celsius, what is its final temperature? Well, we're going to need the specific heat capacity of lead. And there it is, 0.128 joules per gram degree Celsius, 0.128, 0.128, 0.128. So I'm going to write that down before I forget it, 0.128 joules over grams degree Celsius. Now, you might not think to look for that until later, but it's just too hard to do that with the iPad. So what numbers are they giving us? 146 calories. Those units are important. 75 grams, 47 degrees Celsius. So let's write these guys down. 75 grams, what is that? That's a mass. Even if it didn't say mass of, we should know that gram is a unit of mass. Gram only measures mass. 146 calories. What is that? That's heat. That's the Q. And then we have 47 degrees Celsius. Well, obviously that's a temperature. Is that a change in temperature? Is it the initial or is it the final? It says initial. Its initial temperature is. Okay, so we identified the information given. Now we need to know, what are we supposed to do with this? What do they want? They want the final temperature. We're like, okay. Well, we need an equation. What's the equation? The equation is Q equals MC delta T. Now, final temperature is not shown in that equation, is it? But what is related to it? Delta T, right? If we knew the change in temperature, and we've already identified the initial temperature, could we find the final temperature? Yeah. So how about let's solve this for delta T, and then figure out what the final temperature is. You could put delta T equals T final minus T initial into here and solve for TF, but that ends up being an algebraic nightmare for most students, so I don't recommend that. So let's solve for delta T. So we're trying to isolate delta T. So that means we need to divide by M and C, because M over M is 1 and C over C is 1. An equation is like a teeter-totter. When it's equal, it's balanced. And if you do something to one side, you have to do exactly the same thing to the other side for it to still be equal. So if I divide the right side by M and C, I have to divide the left side by M and C also. And that's all we're doing when we're rearranging equations. Then that tends to be kind of messy, so it's a good idea to copy it over. Delta T is going to equal Q over MC. So let's plug our numbers in here. Q is 146 calories. Mass is 75 grams. Specific heat is 0.128 joules per gram degree Celsius. You really do need to write the units in there. Before you calculate, look at the units. Grams cancel grams. Do calories and joules cancel? No. If you don't put the units in your equation here, you're not going to notice that, and you're going to end up with the wrong answer. We need to convert one of those to the other. We could convert the specific heat capacity, or we can convert the heat, Q. I think it's easier to convert Q. So we're just going to take this 146 calories and we're going to convert to joules. We're going to multiply by joules, divide by calories. So the calories cancel out. Dimensional analysis. What's the relationship? 1 calorie, 4.184 joules. So 146 times 4.184 equals 610.864 joules. That number, 146 calories, had 3 significant figures. This also will have 3 significant figures. But we don't want to round it off. We want to just use it like this in our calculation. So we're going to take this guy right here, and put it in instead of that same quantity in calories. So I'm going to erase this. And write 610.864 joules. That's a 6. And the uncertainty is right there. Now, joules cancel out. So what unit do we have left? We have 1 over degree Celsius. So if we bring that up, we basically flip him over. That ends up being equal to degrees Celsius. So I've still got 610.864 in my calculator. I'm going to divide by 75. You need to be careful here. You need to divide by 0.128. If you really, really want to multiply by 0.128, then you need to put parentheses around this whole thing down here. You need to put parentheses around this when you enter that into your calculator. So my calculator is showing me 63 point, it's kind of messy, 63.63. How many significant figures would that result have? It's too messy. Well, this number on top has how many? 3. Those are just carrying along for the fun. This guy has 2, and this one has 3. So this is 63.63, and that would be degrees Celsius. So I'm going to leave the 6.3 in there just because it's a good idea to carry along a couple extra places when you're not finished with the calculation, because we're not done yet, are we? So we need some space. Let's make, oops, not what I meant to do. Didn't mean to do that either. So I'm just going to get rid of this pretty blue box up here so that I can write up there too. So delta T is T final minus T initial, and we're trying to find the final temperature, right? So we would need to add T initial to that side and add T initial to that side. Ti minus Ti is 1. I'm sorry, 0. It's not 1. So the final temperature is the initial temperature plus the change in temperature. That makes sense, doesn't it? Where you started plus the change. So we started at 47. 47 degrees 7 plus this change that we just figured out, 63.63 degrees Celsius, and that has uncertainty in the ones place. I still get that number in my calculator. I'm just going to add 47. I'll write it up here because I ran out of room again. 110.63. Sig figs tell us we should round to the nearest 1 degree, and so we're going to call that 111 degrees Celsius. Now that's what I would call a tricky problem. Solving for either initial or final temperature is just a little more challenging, and they threw a unit conversion in there at us. Any questions?
How did you get 111?
I rounded 110.63 to the nearest 1. Because this is 47, we're adding, this has uncertainty in the ones place, and I'm adding 63.63. This had uncertainty in the ones place that we determined by looking at this. When I get those, I get 110.63, but I need to round it to the ones place. So I round up to 111. You had a question?
No.
Same question? Anybody else? The only way you get better at significant figures is to keep trying. So there will be some questions on the exam that are specifically, do you understand significant figures? And then the rest of it, just give it your best shot. It's better to include too many digits because it's very easy to take a number that somebody, just wrote down off their calculator and round it appropriately. So I would rather you have too many digits than not enough. But you may have already encountered in Mastering Chemistry that sometimes it is really picky about the number of significant figures. Here's another one. When 56 joules of heat are added to 11 grams of a liquid, its temperature rises from 10.4 degrees Celsius to 12.7 degrees Celsius. What is the heat capacity of the liquid? So as with all these story problems, we're going to identify the numbers. 56 joules, 11 grams, 10.4 degrees Celsius, 12.7 degrees Celsius. What's the question? What is the heat capacity? What letter stands for heat capacity? C. So this one we're trying to solve for C. Let's write down these other things and identify them. 56 joules, that's heat energy, which is Q, right? 11 grams, what is that? That's the mass. We've got two temperatures here, 10.4 degrees Celsius and 12.7. One of those is initial and one's final. It says the temperature rises from 10.4 to 12.7. So 10.4 is the initial, that's where it started, and 12.7 is the final. There might also be problems where they just give you the change in temperature. You may say if the temperature changed by 5 degrees, then that would be delta T. But here they're giving us the final and the initial. Well, the equation is Q equals mc delta T. What is the heat capacity? We're looking for C. That's what we want to get by itself. We have to rearrange the equation. C is multiplied by m and multiplied by delta T. To move those to the other side, we do the opposite. Instead of multiplying by m, we divide by m. And we divide by delta t. M over m cancels out. Delta t over delta t cancels out. We do the same thing over here. M and delta t. Now we have an equation. C equals Q over m delta t. So we can plug in our Q, which is 56 joules. We've got our mass, which is 11 grams. And delta T is, maybe we should figure that out, huh? Delta T is final minus initial. So 12.7 minus 10.4, and then it looks like 2.3 degrees Celsius. So that goes in here, 2.3 degrees Celsius. Check the units. None of those cancel out, do they? We're going to have joules over grams degrees Celsius. But that's okay, because those are the units of heat capacity. So 56 divided by 11 divided by 2.3. And how many significant figures should this answer have? Should have 2. So up here, I'm just going to write down a couple extras, and then I'm going to round it to 2. So this is 2.2 joules over grams degrees Celsius. Any questions? One more. I think this is the last one. Let's check. Yes, last one. Last one. If it makes you feel better, I'm tired of doing these two. I did all these problems this morning. Okay. 328 gram sample of water absorbs 5.78 times 10 to the third joules of heat. Calculate the change in temperature for the water. If the water is initially at 25.0 degrees Celsius, what is its final temperature? So let's identify our numbers. 328 grams, 5.78 times 10 to the third joules. There's a temperature over here. Got all our numbers there. What are we supposed to calculate? Calculate the change in temperature, but there's something else too. What is its final temperature? This question has 2 answers. If it asks you 2 questions, or if it says do this and asks you a question, there's 2 answers and you need to provide both of them. Okay, so fine. Let's write these numbers down. 328 grams. What is that? That's the mass. 5.78 times 10 to the third joules. What's that? That's the heat. So you can get clues from the units or from the words. Here it says a 328 gram sample. It doesn't say the mass is 328 grams, but we should know that gram is a unit of mass. It says it absorbs 5.78 times 10 to the third joules of heat. So it's telling us it's heat. We need to know that heat is Q. Calculate the change in temperature. And then it's giving us this 25.0 degrees Celsius. Is that the change in temperature? No, what is that? That's the initial temperature. So we're looking for the change, delta T, and we're also looking for T final. So our equation, Q equals MC delta T. We want to solve this for delta T. So we're going to divide by M and divide by C, so they cancel out. Do that on both sides. Delta T equals Q over MC. Okay, so Q is 5.78 times 10 to the third joules. M is 328 grams. What is C? 4.184 joules per gram degree Celsius. Where did that come from? That came from the table. The problem tells us this is water. We need the specific heat capacity. The equation tells us there's a C in there. We need the C. They didn't give us the C. Go look it up. In the table it says the specific heat capacity for water is 4.184 joules per gram degree Celsius. Check the units. Joules canceling, grams canceling, degrees Celsius will be left, so that's good. 5.78 EE3 divided by 328 divided by 4.184. So the change in temperature is 4.2117. How many sig figs should that have? 3. The mass and the heat both have 3, and so that would be right there. 3 significant figures. So this is one of our answers. So like if this was on Mastering Chemistry and you needed to put in both of them separated with a comma, let's pretend that this is our answer box up here. We would then round that for that answer. Let's see. So change in temperature equals 4.21 degrees Celsius. And the final temperature equals, well, the final temperature, we've rearranged this before. It's the initial temperature plus the change in temperature. So it's 25.0 plus 4.2117. I still have the 4.2117 in my calculator, plus 25. 29.2117. That's degrees Celsius. How many significant figures should that one have? Or maybe it's better to ask, in what decimal place is the uncertainty? 25.0 has uncertainty in the tenths place. This 4.2117, we had said had uncertainty in the hundredths. So this is going to have uncertainty in the tenths place. So we would record our final temperature as 29.2 degrees Celsius. Any questions? So that's the end of chapter 3. These are the review slides.